I was going to do a concluding part on this presentation by taking you through the whole IF domain as a kind of a system type situation. So just to recap what a lot of what has already been said perhaps, but I'd like to go through the superhet circuit just very briefly and then concentrate on the IF, which as Greg has pointed out, is this which is this part of our circuit. And we're going to really come back and we're going to analyze right from here through right to here where the detector is, and then go down to the AVC and the audio takeoff and tell you how that works. Because knowing how it works then is a key or is a guide to troubleshooting the thing when you have problems. But anyways, so going up to the front end here, you recognize that as the mixer oscillator. It's a pentagrid converter called a 12BE6 here that works in that fashion. And as Rick pointed out in his presentation, there's heterodyning going on between an incoming signal and the local oscillator that beats together. And it actually produces four frequencies: the original fundamentals, as well as the sum and difference. And as Rick pointed out, the designer usually takes the difference on the high end. So the local oscillator is working away at 455 kilohertz above the incoming signal. Both are tuned so that they track together, and you always have that 455 kilohertz difference coming out of here. The operation, the heterodyning operation in the mixer oscillator takes place because when two signals are combined in a nonlinear environment, they mix together in a heterodyning effect that produces the sum and difference frequencies. In an audio circuit where you have mixing, and everybody knows about an audio mixer, you have two linear analog signals coming in to a linear environment, so they don't heterodyne together. And that's the difference between a radio heterodyning and a mixer, an audio mixer. It's an important difference. When we get into audio circuits later, we'll talk about that. When audio circuits misbehave, there is some heterodyning that takes place in them, and that's called intermodulation distortion. And that's something that you want to avoid and get rid of. But anyway, so we're not going to spend too much time on that. We're going to go in here to our first IF, and as already pointed out, the IF transformers are working on a 1-to-1 ratio between primary and secondary, and they're tuned to 455 kilohertz, has already been adequately demonstrated. And so the 455 kilohertz, which is then present, especially here, is fed into the first IF amplifier. And it's interesting to note that all of the gain of the radio part of the circuit is right in there. The mixer itself hardly has any gain at all. You'd be lucky if it has a gain of 1, because it's devoted to the heterodyning effect, and you don't get much gain out of that. So what are you getting out of here? Well, you're getting 400, a gain of 400 or more. And most of your radio, then your radio signal amplification takes place right here in the IF stages. And that's why I guess that one is so important and why we're dealing with it. Because when things go wrong, and they go tragically wrong. And then from there we go into the second IF transformer and into the diode. Now there's the little diode that is part of the internal circuitry or configuration of the 12AT6, which is a dual diode, single triode, fairly high gain triode to give you your first audio amplification. Now I do have a slide that talks about this part of the circuit, and we need to just focus on that for a minute or two. So you've seen this figure, this signal pattern before, and say you're tuned into a 1 megahertz radio station, then all the little dashed lines here represent the 1 megahertz carrier, and the audio modulation is the envelope riding on top and on the bottom. There's a positive audio modulation going beyond a 0-volt reference point or line, and the negative audio modulation. And the purpose of the diode detector, and it was mentioned before, I guess when we talked about regenerative radios, is to strip off one of those, because otherwise they would cancel when you get the audio detection. So you only want one part, and you choose to strip off the top part. How do you do it? Well, if you go into the diode part of the 12AT6, what happens is that this conducts, this turns positive only on this portion of the modulated carrier, and it essentially shunts it to ground. So you're left with only the negative going portion here, and so you have a negative reference. You still have part of your carrier running along here below the 0-volt line, and it'll be -2 volts, or it varies depending on signal strength between 2 and 5 volts or so. But nonetheless, the important thing is that it's negative going. And so the signal comes down here through the secondary of that IF, that last IF transformer, and then it hits this capacitor. Now this is an RF filter, and it gets rid of all of this stuff. So it basically decouples that to ground, and then you get to a point and we'll go back to the radio schematic in a minute, where there's an AVC split off, an automatic, it's automatic volume control or automatic gain control, essentially the same idea, and that splits off from the audio. So at this point you have only the audio envelope, and you got it down here, and now you want to do something with it. You either want to take off an audio, or you want it to deliver to an automatic gain or volume control. Okay, so if we can go back to the schematic. Okay, we're up here, and we've got our detection in place. Comes down there. That's about 100 picofarads. Sometimes it goes as high as 200 picofarads, but if it goes higher than that, you start to shunt your audio portion to ground. You don't want that. And this side of it is ground. In the 12AT6, you notice that one diode is also grounded. Sometimes they just bridge them together, and you got both diodes paralleled, coupled. Other times they might pass one of the diodes to some other part of the circuit, but you don't have to worry about the details there. The idea is that you have your detection in place. So, all right, we come down here. We've got rid of our 455 kilohertz carrier there, or pardon me, it is a 455 kilohertz carrier at that point. And you come down here. Here's the AVC split off. So you'll notice there's a very high meg, a very high value resistor here, and quite a hefty capacitor down there. What that does is it filters out the audio portion, and you're left only with a varying DC portion. The purpose of that is to provide a negative bias, and you follow this line over through the loop into the grid, the signal conducting grid of the input tube. And that signal varies negatively corresponding to the strength of an incoming signal or a radio signal that you want to detect. Now the beauty of the AVC circuit, of course, is that it's an automatic gain control, and the stronger the input signal, the more negative this becomes, and the more the negative bias turns down the gain of this particular part of the circuit. And this one too, because you'll notice there's an AVC going into the grid of the pentode for the IF amplifier. The interesting thing about it is that you can't do anything about a weak radio signal with an AVC circuit, because you just don't have enough signal in the first place to deal with. So it's mainly beneficial when you have a strong local signal. A strong local radio signal may be as high as 100 microvolts coming into the antenna. Like if you get 630 on your dial or something like a very powerful AM signal is coming in. And the AVC works to tune down or to attenuate that particularly very, very strong signal. And then it also, in variations of that signal, tends to even out the amount of maximum and minimum associated with the audio variations on that signal. So that's what the automatic gain control or automatic volume control does. All right, so we're down here, and we said there was an audio split off, and here it is at this point. Then it comes down. This is shorted out because this is a phono input. This disconnects this portion of the circuit when you plug in a phono. a phono input, like a record player or something, and then it goes straight into the audio portion. But otherwise, through the internal connection on the plug itself, this is connected audio-wise through here. You'll notice there's one more RF filter there, just to make sure you've gotten rid of all of your RF component coming down here. And then you're coupled directly into the volume control, and you vary the volume of your radio, and you're getting pure audio at this point, or you should be, and it's being delivered to the grid of the first audio amplifier, and then out it pushes to the power output. There's very little gain in this as well. You might have a gain of 100 or so in this part of the circuit. Might have a gain of a few, it's low, maybe what, 10, 20, it's hard to say. It's low. And but when you couple all the gains together, you can get gains then of 40,000 or more in a radio receiver like this. So this is not a long distance type of receiving capability, but it's very, very satisfactory for most local radio stations. And essentially, that is how all of this works. So now what I would like to do is get all our heads together and let's try troubleshooting something that can happen, particularly in this portion of the radio. There. Now I just tossed some of my pieces of equipment out on the table here and took a picture of it because, and we'll deal with budgets when it comes to this, because if you're getting new into radio restoration and that, you're always thinking, yeah, okay, there's all sorts of expensive gear out there, and I can't afford everything, at least to start with, so what do I do? What do I need in order to restore a radio? And so here are some of my pieces of equipment, and I'm not showing oscilloscopes and signal generators at this point because you're into the more expensive items. They're really nice to have, and sometimes you absolutely might need them, but I'm just showing what you can actually get along with if you're on a budget. Now here's an old ICO signal tracer that I use. Heathkit produced one as well, and this is the made-for instrument that you would really like to have, but they're no longer available. And this has got everything. There you see a probe, that's an RF probe with a detector in it, and that plugs directly into your IF and RF for signal tracing. And a signal tracer only traces the signal through, it doesn't inject a signal into the radio circuit itself. So you can only trace the signal as it progresses through and gets amplified right throughout the radio regime. And you also have an audio input for just dealing with the audio portion. This goes straight into the audio portion, the audio amplification portion without any RF detector in place. And then there's a ground lead running here as well. So you got a bunch of wires. Now, this is a particularly sensitive amplifier inside. It's got a two-stage 12AX tube, so you get about 10,000 gain right in the input of this circuit. And you need all that gain in order to go all the way down and look at the radio and go right up to the weakest parts of the signal incoming into the radio circuit. And then it goes into, I think it's a 6AQ5 as an output that drives the speaker. And you get another, some other gain, another 10 or so from that. So you've got a high gain, dual purpose RF tracer, signal tracer, as well as audio signal tracer. And you even got some other capabilities here where you can substitute an output transformer and all that jazz. You've got a little Magic Eye indicator for signal strength and that kind of thing. So this is really nice to have, but problem is they don't make them anymore. Now if you go to this little box, this is a little box that was made by Micronta, which was a brand that was offered through Radio Shack back in the day. And this does the same thing as that, only it's much smaller, and it's a transistorized amplifier inside. Now, it's okay. It's got an RF detector in it. This lead here goes to, well, there's just a couple of test leads here with banana clips on them. There's an RF input and an ordinary audio input as well, similar to what this guy has. And you have a volume control. The problem is if you want to use it for vacuum tube radios, you got to watch, and you can re-engineer it a little bit yourself if you want. You got to go in, and you've got to, there's an internal diode in here, RF detector diode. You've got to go in and you've got to maybe reduce the signal strength at the output of the detector diode and make sure that your coupling capacitor in the input is capable of handling the voltages that might be present in a radio. So you want to have a high voltage capacitor, maybe a 0.01 of 400 volts or so, and you can rejig this thing in order to make it work for both types of radios, transistorized or vacuum tube. Okay, yeah, and and here's an ordinary digital multimeter, which is what you absolutely need if you're going to be in this business. Here's a more expensive one that also has a capacitance reading circuit on it, function on it. So these you can get for sometimes $20, even in Canadian Tire or Liquidation Warehouse. You can pick up really cheap DMMs these days, and they're perfectly adequate for all of what you will do when you start off with radio. These are more expensive, and you're looking $50, $70 in eBay and so on. Then here's a couple of substitution boxes, which are really nice to have. Resistor and capacitor substitution boxes. Now these are old guys, so you might want to just go in and check the values, might have to replace some of the capacitors and that, but are really nice to have when you're substituting values in a radio and you're tracing signals and you're trying to see what happens when you vary the values of something. This finally is an MK168 component tester. You can get them on eBay for $30. They're absolutely worth the money. I've checked all sorts of values with them. They seem to be fairly accurate. Now, it's not all of the component testers on eBay are accurate and dependable, but this one seems to be, at least it has been for me. So it checks resistors, it checks capacitors, it even gives you values of inductors up to 100 millihenries. So for most of radio work, except for the power transformers and so on, or chokes, it'll tell you the value of the inductors as well as the capacitors, and they're accurate to within 1%, 0.3% sometimes. And they also give you effective series resistance on electrolytic capacitors. They'll test that for you. It shows up here on the display screen. It gives you a pin readout as to which pin represents what part or electrode or component in the thing that you're testing. It's got 3 leads, so you can check transistors, you can check field effect transistors. It'll even read out a Zener diode, but only up to 5 volts of breakdown voltage, and some other stuff as well. So these little boxes for $30 are a real steal deal. Now, okay, so what do you absolutely need? Okay, if you don't have one of these or the Heathkit variant, you might say, well, I can't do it. I won't have one of those. And these are no longer made either. But I can get one of these. That's going to be helpful. I can get an ordinary VOM, a DMM. And I can't get these, but you'll want to have a few resistors and capacitors around so you can do your work. And that's all that's necessary. So you got to come up with some form of signal tracer. You got to have a DMM. I would highly recommend you get one of these, and you have some parts and tools and the soldering iron, and you're ready to go. You got everything for what? An outlay of $30, $20, $50, parts and components. But what do you do with the signal tracer? Okay, I have a suggestion. Okay, so here's an idea for you. Now, it's pretty easy to come across tuner amplifiers of the component variation for 20, 30, $40 or so these days. Good ones. And they will have to have a CD input at the back and a tuner input. And they have a good audio amplifier in place. Now, the reason I say CD or tuner input is because those are high gain audio inputs. And all you need is an RF detector in the front of them. And you can make those work as a very effective signal tracer. So you probably, I hope you know what I'm referring to, the radio tuners that are the component radio tuners that are around now, and things have moved on from that day, and you can get them for a good price. David has a number of them, so cheap but of good quality. Of course, they're all semiconductors, so you don't get a vacuum tube signal tracer out of that. But here's what you can do. You can take this circuit here, you can make your own little probe. Now this is the probe and the components inside of the ICO probe, RF probe. See, it has a germanium diode there. You can make your own probe. Get a even a pen case and stick a nail out the front end or a needle, glue it into place, couple your diode, and there's a dropping resistor here. That's 470K. You might have to adjust that for your particular circuit. And then have a little metal utility box in which you connect with a coaxial cable into your input, and you have a volume control. And then a capacitor, 0.01. Here's the high voltage part of it. You know, specify that you've got a good high voltage capacitor in there, and that goes out to the input of your tuner amplifier. And you will have with this, what will this cost you to make? Maybe 10, 20 bucks, I don't know. Depends on how many parts you have in your junk box. And you can couple that to your tuner amplifier. And you've got everything you need then. So now our budget's in under $100.
So the 1N34 would work the same, I guess?
Yeah, you could. That's
I've never seen a 48.
48, yeah, okay. You just have to watch out for the PIV, the peak inverse voltage on a 1N34. But some of them are good for up to 60 volts, I believe, going from memory. So
stick that diode
On the plate circuits.
B plus, eh?
well, that's why you have the dropping resistor in there, and then that's why you have the isolating capacitor as well. So you're not feeding directly high voltage DC into your input. Can we go now back to the radio circuit, to the AC/DC circuit? I wanted to go through a troubleshooting analysis of the IF section in this. So we'll have to hurry up a little bit, and we can't cover it with all the detail that it would be nice to do maybe another time. All right, so I'm going to start with the assumption that we know that the power supply is working okay. You've measured the voltages here, and for an AC/DC radio, they could be up 120 volts or so. There's a dropping resistor here. These dark lines are all representing the B plus high voltage lines going to the radio. So it's nice to see that, and that sets it all apart from the other circuitry. All right, so we know that this is working. Let's just assume that. We also know that the input of the radio is working, just to eliminate the possibilities. If you wanted to do a quick check, of course, you could take your signal tracer with the RF detector on it and put it here, right there, and see whether you're getting a good signal. Now, you'll have to have lots of gain on the signal tracer at that point, because there's not much coming in there, 100 microvolts on you tune it, of course, to a strong local radio source, and you're going to pick up a signal. It might be a little weak, but you'll pick it up if it's working. And so if you don't get anything there, what do you think? What could be wrong?
I'll put a new 12E6 in there.
Okay, you could do that. Oh, I should have said we assumed that you've already tested the tubes. However, you shouldn't assume that because you test them, everything is just hunky-dory with them. What kind of a tester do you have? Well, that's another thing I guess you need. If you have an emission tester, you may not have really correctly identified that the tube is working, because all the emission tester does is tell you how much conduction you have across the tube. It doesn't tell you how well it amplifies or carries out any other function. If you have a mutual conductance tester, you would get a better clue as to whether it is capable of amplifying. But even that only tells you it's capable of amplifying at 60 hertz, because that's the test signal, or 120, depending on if it's rectified. That's the test signal in a mutual conductance tester. Those are the shortcomings of tube testers. So it is always good to have a set of good tubes on hand so you can substitute them. And so we go back to here. You don't get a signal. Were you going to suggest something else, Greg?
I was gonna say check the tube first, but
Okay. All right. If you don't get a signal there, what else could be wrong?
Broken wire.
antenna loop could be open.
Okay,
Running,
we're assuming though, we're going to assume that the input stage is working
and the oscillator's running.
and the oscillator's running.
So it's the transformer.
Well, I guess you'd have to check the IF transformer.
Yes, okay, yeah. So you might say, well, okay, either something is shorted out in the IF can or it's open. And I think in Rick's presentation, he showed us very well just how you can do that. But if you don't have a scope, you have your signal tracer and you set it here, no signal. And you might go here and say, okay, and you might be getting some jumbled radio signals, but you're still getting something. So something has happened between here and here. And the possibilities are that you have a shorted turn or something in the IF can and it's collapsing the inductive field, or you have an open IF can. Well, if IF coil, but if you have an open IF coil, what test can you do?
Take a capacitor from the primary to the secondary and jump across it, see if it, I don't know.
Okay, but you want to find out if there's a problem in the IF.
Oh,
So what do you do?
ohmmeter.
Ohmmeter, right, yeah. So you got one of those, you got your DMM. So you'll check the coil here and you'll find out if it's open or not. You check the coil here and find out if it's open or not. But, of course, we said this was working, so it implies that this part of it is working. Because otherwise you wouldn't get B plus voltage on the 12BE6, it would collapse and you wouldn't get any input stage working for you. You wouldn't get any radio signal. Okay, so there we are. That might cure that problem. You find out that it's not working because you have an open cap. But let's say that now you've discovered you've got a signal there and it is what you expect it to be at 455 kilohertz, and it goes into your first IF amplifier. Okay, all right. So then you say, great. Now you go to the back here and you put your signal RF probe on here and you don't get anything. Okay, what could go wrong? What's happening? Okay, yeah, okay. So the next thing you'd probably do is, well, let's check the plate voltage. So you check the plate voltage here and says, by George, it's no reference to this George. It's about 70 volts.
This is bygone George.
70 or 80 volts, so okay. So at least you know you're getting conduction through the IF primary, and yet you're not getting a signal there. Well, wouldn't it suggest that maybe you better try substituting that tube and see if perhaps that's the reason. Now you can say, yeah, but it checked good, but once again, remember your tube tester limitations.
The best tube tester is right there.
Yeah, right, because the one thing about using instrumentation is you also have to realize the limitations of the tools you're using. If you're a carpenter and you get into a job and you find out you have a hammer with too short a handle, you know that it's not going to do certain jobs. It'll do some, it'll put some nails in, but there are other aspects of the job it might not be capable of doing, and that's the case here. All right, so you substitute the tube, and there it goes, it's working. What could have happened? Even though the tube tested okay on an emission tester, you could have an open element inside, you could have a shorted element, and let's say, however, that you've put another good tube in there and it still isn't working. What's the next thing you might think of?
Capacitor.
Which capacitor?
There's no capacitors in there.
That one
has cap.
In the IF transformer.
Yeah, no, you don't know that this capacitor has failed yet. All you know is that this stage is not working. Even if the capacitors failed, you would get a signal out here of some sort. You would find something. You wouldn't be totally dead. So, and then you put in a good tube, and it's working. Pardon me, it's not working yet. What else could be wrong? Well, okay, I won't drag it out, but you better start looking at the connections in the circuit. Are the values in there correct? Has somebody got in and monkeyed with the value, changed it around? Is there a short somewhere in the circuitry? Even in the socket itself, is there a leakage path or a short path in the socket connections? Those are all possibilities. They're a little more rare, a little more infrequent, but there's something that you have to keep in mind, just in case you need to fall back on that. And okay, so let's say that we've now discovered that everything else is okay, and you get a good signal here, and you jump over to here, and you don't get your signal anymore. What's happened?
There's something wrong with the IF transformer.
Could be something wrong with the IF again. Right, perfect, yeah. So you could have an open, you could have a short. Even a single turn short in an IF transformer will take you down. I think also in Rick's presentation he showed the effect of that. You know, you could kill your output signal on the back. Even if you have a shorted turn, it doesn't have to have a whole number of turns. Even a single turn will do it. It will collapse the inductive field and you'll fail to get a signal. Now, so let's say you do get a signal, and you're now going into the detector, and the detector is going to shunt the positive going portion of your modulated carrier coming in, which is at 455 kilohertz, of course. We saw that in the other slide. You're going to have a path of the demodulated signal coming down through the secondary into the RF decoupling or filtering capacitor here. Okay, so you get down here. Now, Rick and I were working on a radio, and we found out that we were getting an audio signal down through this line here, but it was distorted. It was garbled, and you were getting... What could be wrong? In this part of the circuit, what could be wrong?
Capacitor? Coupling capacitor? Or
Yeah, okay. You know what we found? Was that somebody had substituted the 100 picofarad cap here for one that was 500 and some picofarads. And what it was doing, it wasn't shorting out all of the audio, it was only shorting out the high frequency portion of the audio spectrum. And so it was garbling the signal. So somebody had changed the circuit previous, and a problem with a lot of antique or old radios is that people have had their hand on them over the years. All right, so when that was replaced, that restored the operation and you got decent audio. You come down here, and now what kind of AVC or AGC problems can you have? Well, this circuit might not be working right. Now here's where you want to get in, and you could use your substitution box if you have it, or at the very least what you should be doing is checking the values, especially in old radios. You know, here's a cap that you'd be maybe wanting to replace, if not all the others. And this represents an RC circuit. So it's a type of filtering circuit which will eliminate or pass to ground the audio portion, the strong audio portion of the signal that you want. And this RC represents a filter that will allow very low frequencies to pass through, but enough that it will track the signal variations coming in and then powering up the automatic volume control circuit. So if you're finding out that you're tuning in a radio and you get excessively loud input signals on local stations, the AVC might not be working, and you want to go in and check these values. Maybe you have to replace them. If they're more than 10% off spec, I would say replace them. Like resistors tend to increase value with age. They heat up and gradually the value increases. And if you check a value and it's more than 10%, definitely replace it.
It's pretty hard to heat up a 2.2 meg resistor. You need a lot of voltage to heat that up.
Well, it is, but they vary in
radio.
the external temperature around it. You know. Yeah, good point. And so I'm going to leave it off there because our time is well up, and we won't get into the audio portion of the radio and what can go wrong there and how you would troubleshoot that. And I haven't necessarily touched on all the problems that can occur there, but we've touched on the main ones and the main considerations. So I hope that this is helpful. Okay, well, we're going to have to draw our meeting to a close. And I thank all of you for your comments and your inputs into the discussion today. I thank the other presenters, Rick and Greg.